We start with Mr. Brian Greene, who presented that in one of his series. Okay, and that's why I want to put this fellow here. Brian Greene, this is his brief bio. I got it from different sources. Is a string theorist and mathematician. Greene was a physics professor at Cornell from 1990 to 95 and has been professor at Columbia since 1996. So he's been around for a while, right? What, 28 years now? He is chairman of the World Science Festival, so he's quite popular, right? Also a popularizer of physics, so-called physics, mathematical physics, irrational physics, right? Greene has become known to a wider audience through his books for the general public, The Elegant Universe, Icarus, etc. The only one I'm going to mention there, The Fabric of the Cosmos, because I'm going to be looking at his, I think it was his fourth series, installment on that series, and that was, he talked about space. But in that same space that he analyzed, he talked about time. And why? Because he talked about the gravity probe B, which was used to put, to know where to put the satellites up there, for GPS. So it was an important experiment that showed where to put the satellites, but it does not explain how all that works. So to this day, none of these people can tell you, how GPS works. They tell you, look, all we know is that when we measure, there's a difference in time when you put the atomic clocks in those satellites up there in the sky. They have no idea why. What causes, the clock to go slower or faster, the ones on Earth versus the ones up there. Okay, so what we're looking for is explanations, mechanisms, causes. We want to know why. And that's an answer that no mathematical physics on planet Earth, with all the GPS we have out there, can answer for you. Okay, so that's the issue. Okay, the issue is mechanism. Okay, that's what we talk about here. We talk about physics, not math. Okay, and when they tell me that time is dilated and time is bent and I don't know what, they're not talking about physics, because time does not belong to physics. Physics, we do not use time because time is a description, and in science we explain. We do not describe. Okay, so here we have, this is what he tried to show, that NASA gyroscopes prove Earth drags what? Time around itself when it spins. My God, it drags time around. And you say, Bill, is this true? Is this what they try to show? Well, here's a picture of what they're suggesting, right? Time is being dragged around. Okay, if this is what they think, what are they dragging? The seconds, the minutes, the seconds, right? So we need to know what they're talking about. And here's from respectable sources, authorized sources. Here you say it. This is NASA, frame dragging experiment, okay? And it says direct evidence that the Earth, drags space and time around itself as it rotates. Now, I didn't invent that. This is out of authoritative sources. The research is the most accurate direct measurement to date of the effect, bizarre effect of general relativity, which predicts a rotating mass will drag space around it. So every time you turn around, you're dragging space. Forget about air, but you're dragging space as well. Okay, I guess you got to spin fast enough to notice the difference. As the Earth rotates, it pulls space time. So it's got to pull time as well. Okay, I want to make sure they like to talk about space and they leave the time usually out, because if they just talk about dragging time around, people would say, "Ooh, that doesn't sound right." But when they say space, people think it's a physical object. And so, they can get away with more by saying space. But here we're going to show that they're talking about space and time, and they call it space-time. And what they're really talking about is not dimensions, not coordinates, not vectors. They're talking about number lines. What they're dragging around is number lines. Okay, so here's the gravity probe B on the right. It says, this comes from the Wikipedia. The gyroscopes were intended to, reveal how space and time are warped by the presence of the Earth and by how much the Earth rotation, drags space-time around with it. Now, I didn't invent this, okay? This is out of all these sources, right? And then at the bottom, there's another source there. It says, in general relativity, mass rotation influences the motion of objects in its neighborhood, Put simply, the rotating mass drags along space-time in the vicinity. Okay, now, what is it that I didn't understand? Okay, yeah, they're saying you're dragging time around, and you're dragging space around, which is nothing, but they claim that space is this physical object, three-dimensional object, and so people get confused. They say, well, yeah, I can probably imagine it dragging a three-dimensional object around. But when you say just time, they say, what do you mean you drag time? And that's why they don't talk so much about time. They talk more about space. And just in case, here we have Stephen Hawking. He clarifies for us, just in case you missed it, that space and time, there are no differences between them in the religion of mathematics. Okay? And here it is. He says the following. He says, in relativity, there is no real distinction between the space and time, what? Coordinates, meaning number lines. They're not talking about coordinates. They're not talking about length, width, and height, or about latitude, longitude, and altitude. They're talking about radius, width. They're talking about numbers. And what they're talking about is number lines. And they call them dimensions or coordinates or whatever word they put in there. Okay, so they're saying there's no difference between space and time coordinates, meaning number lines, right? Yeah, of course there's no difference, not in number line. There is a difference between a coordinate and a dimension, but the mathematicians never figured it out that coordinates and dimensions refer to different things. Dimensions refer to, length, width, and height. There's perpendicular directions in which an object faces or points. And coordinates, the arrows go in the opposite direction. They go from the walls of your house towards you. That's your location with respect to your house. If you take three perpendicular, arrows coming towards you. Okay, so that's different. But mathematicians treat coordinates and dimensions and time and everything all the same because they're all number lines. They're not dimensions. Okay, so where does good old Brian Greene start when he talks about this subject about dragging time around? Well, he starts by showing that there was a little bit of a difference between Newton and Einstein. Okay, so let me put this up here. And what I've done is I've karaoke'd it behind. So all these will have my voice in the background, but they're the exact words used by Brian Greene in his exposition, in his series. So here it goes. Listen carefully. There it goes.
Back in Newton's time, space was just a container. It didn't do anything at all. Then, through Einstein, space begins to affect how objects move.
Okay, so they're starting with Einstein, right? He's starting to treat space and time. Keep in mind, they're talking about space-time. They leave the word time out because that would create a little bit of a problem with a lot of people. And so they talk about space being able to move and shove things around. So now it's no longer this static thing. It's got this ability to push things around, okay? And here he rubs that in. Again, let me show you this. Here it goes. Listen carefully.
Where Newton thought space is passive, Einstein saw it as dynamic, interwoven with time, and it dictates how things move. So, after Einstein, space can no longer be thought of as a static stage. It's an actor, and it plays a leading role in the cosmic drama.
Okay, and here you can see this comes from Stephen Hawking's book, and he does say that space and time do actually move. So, there's no contradiction between what Brian Greene says and what Hawking says. He says, before 1915, space and time were thought of as fixed arena. But then he says space and time are now dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time. And in turn, the structure of space-time affects the way in which bodies move and forces act. Okay, so you see this argument from mathematical physics. So they all agree, the mathematicians, the so-called mathematical physicists, they agree that they're saying space and time move and they have the ability to push things around. Okay, that means time pushes on you. They're treating time as a physical object. Let that be no ambiguity about that. In fact, if you're going to drag time around, which is what Gravity Probe B essentially proved, frame dragging as they call it. If you're going to drag time, it had better be a physical object. And so that's what they're saying here, okay? I want to make sure everybody understands that. They're saying that time is a physical object, like a rock, or like a tree, or like a dog, or something that you can drag, right? Okay, and here he continues. He says, space is not nothing, meaning time, right? Remember, it's space-time, right? He's saying it's not nothing, it's something. And here it is. This is all out of their own, this is the horse's mouth speaking there. I'm just speaking in the background because I'm just saying the same words that they're saying. And this is all textual. This is all verbatim. Here he goes. Listen carefully.
What if you took away all the planets, stars, and galaxies? And not just the big stuff, but tiny things. What if you took it all away? What would be left? Most of us would say nothing. And we'd be right. Strangely, we'd also be wrong. What's left is empty space, and, as it turns out, empty space is not nothing. It's something. Space is so real that it can bend, space can twist, and it can ripple. So real that empty space helps shape everything in the world around us and forms the very fabric of the cosmos.
Okay, so there you have it. Space and time are physical objects. And he reinforces that throughout his whole exposition, his whole lecture, his documentary. Okay? And just in case, he wants to show you an argument that he's got of why space and time, remember space-time, but he's going to talk mainly about space, but don't let that confuse you. He's also talking about time. He's saying that this thing he called space, this thing he called space-time, is a physical object because otherwise, you have a skater and she's skating around. What is she moving around with respect to if you remove all objects in the universe, all atoms, everything? And here, this is the horse's mouth talking here, okay? And let me put them on. Here it goes. Listen carefully.
Let's imagine that you could take all the stuff in the universe so that the only thing left is a skater spinning with respect to completely empty space. If the skater still feels her arms pulled outwards, she'll know she's spinning. But if empty space is nothing, what is she spinning in relation to? When she spins, her arms play out because she is spinning with respect to something. And that something is space itself. Scientists came up with a bold new picture of space. The key was to make something out of nothing.
I absolutely love that last statement. Yeah, they had to make something out of nothing. So we have nothing out there, but they said, well, if she's spinning, what is she spinning with respect to? And that's why they turned space, time, right, into a medium. Because otherwise you say, well, what is she spinning with respect to? And so they had to turn nothing, which is space, what space is, or not, into something. That's what happened. Okay, and just in case he comes up with another bit of proof, evidence, and that is that all atoms are mostly empty space. Okay, so here goes. Listen carefully.
You can take the most abundant thing in the universe, even the tiniest of things, like atoms. Even they are almost entirely empty space. In fact, if you remove all the space inside all the atoms making up the Empire State Building, you'd be left with a little lump about the size of a grain of rice, weighing hundreds of millions of pounds. The rest is only empty space.
So where did they get that? Well, they say Rutherford ran some experiments. What was it, 1919? And he figured out that an atom is mostly empty space. And everybody just repeats that today without thinking about it. If an atom is mostly empty space, meaning there's a ball in the center and a little bead going around it, you have to explain why the bead doesn't fall, negative bead falls to the positive nucleus, or why the negative bead doesn't spontaneously fly away. They never explain that. They just say it's mostly empty space, meaning between the electron and the proton. And that's just a statement. It's an irrational statement because they can't justify why that bead stays faithful to the proton, despite being, one positive, the other one negative. It should fall directly to the nucleus, or why does it fly spontaneously away? And of course, they'll never answer that kind of question. But it turns out that if an atom is mostly empty space, what is space? Well, it turns out that space, according to them, is made out of particles. And again, this comes not from me, okay? This comes from good old Brian Greene in his show, and here he goes. Listen carefully.
According to the rules of quantum mechanics, even if you try to remove every last atom and particle, you'd find that empty space is still far from empty. In fact, it's teeming with activity. Particles are constantly popping in and out of existence. They erupt out of nothingness, quickly annihilate each other, and disappear. In quantum mechanics, empty space is not that empty. It's full of fluctuating fields, full of all sorts of jittery things going on. It's a place where particles are constantly fluctuating and annihilating each other, and being created again and annihilating. It's a place of chaos and bubbling.
So what is empty space made out of? It's made out of particles. So we have particles such as an atom, which is mainly empty space, and then empty space is not empty because it's made out of particles. Great. I mean, we've learned a lot with these people, okay? Okay, so they ran this gravity probe B thingy, and they proved with it that space is a physical object, meaning space-time. Keep in mind, this always includes time. They just don't mention time because it's taboo. It's kind of more obvious if they just talked about time, so they talk about space, which is easier to push across to people. Okay, so this is what he says about it.
This experiment buys the most direct evidence ever found that space is something real, a physical entity, like a fabric. After all, if space were nothing, there would be nothing to twist.
So yeah, if you're going to twist space, like he said originally, that you could twist it, bend it, send waves through it, well, if you're going to twist it, it had better be a physical object. So I think there's no, I mean, he reinforced that in so many ways that you cannot say he did not say it. He did say time, space, space, time, physical object. It's a thing, okay? He never defined what a thing is, but he's saying it's a thing, meaning you can touch it, because he's saying space can push on you, meaning space-time can push at you, meaning time can push at you, because time and space both move, and they're malleable, and all these good things. Okay, so here they came up with this experiment to prove to people, to the general public, that space and time are physical objects, and you can actually drag space and drag time around the Earth, and it's called Gravity Probe B. That's how they're going to do it. And he gives you a little light explanation here there, but it really puts you up to date what the gyroscope, what your $1 billion, it was around 800 million, but this is, I think, conservative. I think they spent like $1 billion over like 30 years to develop this project. And this is what he's got to say about it. So this was the plan. They did it with these gyroscopes, perfectly round gyroscopes, and they're going to point, the axis at a star, and so they're going to try to figure out if when Earth moves around, it drags these gyroscopes in such a way that it takes that axis off, pointing to that star. And I think they did it with a laser. Okay, here goes. He's going to explain it in more detail. Here goes.
Normally, a gyroscope's axis points in a fixed direction. But if Earth is actually dragging space, then the gyroscope's axis would be dragged along with it, shifting its orientation in a way that could be measured. NASA attached 4 freely floating gyroscopes to a telescope aimed at a distant star. If space twists, then over time the gyroscopes would no longer point at the star, since they get caught up in the swirl of space.
Okay, so that was the plan. That was the design of the experiment. They had a little bit of problem. They had a little bit of a problem because you really want to control that. You want to make sure that there's no change for some other reason that has nothing to do with the Earth dragging time around. Okay, so that was the issue. But it turns out they encountered a problem, and he states it. At least they were honest about that. And I want you to consider this when you factor whether they were honest or not, or whether they, kind of fudged the data to match what they wanted, their preconceived ideas for this. And here it goes. Listen to this.
For over a year, Gravity Probe B orbited the Earth, while NASA monitored whether the Earth would actually twist space. The data began to trickle in, and there was a problem. The gyroscopes were experiencing a tiny, unexpected wobble. And to clean up the data would cost millions. Over the next 2 years, the problem with the data was solved, revealing that the axis of the gyroscope shifted by almost exactly the amount predicted by Einstein's equations.
So there was a problem, and the problem was a big problem because we're talking about wobbling, and kind of like, that was what they were testing. And so if it's wobbling for some other reasons, then your experiment is all shot out. It's no good. But they're saying they cleaned up the data. You know what I mean? They cleaned it up, and they got rid of all the bad data. And it turns out, just by sheer coincidence, the deviation from the axis matched Einstein's equation. Coincidentally, what a coincidence, That's something you should keep in mind, okay? Personally, I don't know whether it did or not, whether they fudged the data or not. It seems like they did, but I think it's irrelevant anyways, because, again, their conclusions are what's important. And you would think that after all that testing, after doing all these experiments and looking at Einstein's equation about space and time, you would think they'd have a great handle on both space and time. Okay, so this is how good old Brian Greene concludes his presentation, and you really should listen to this, because this is his conclusion. This shows you how much they learned from all this about what space and time are. Okay, and here it is. This is how he ends his presentation. Here goes.
For something that is a vital part of our everyday lives, space remains kind of like a familiar stranger. It's all around us, but we're still far from having unmasked its true identity. That may take 100 years, it may take 1,000 years, or it may happen tomorrow. But when we solve that mystery, we will take a giant step towards fully understanding the fabric of the cosmos.
Okay, so after all that, he has no idea what space or time are, what space-time is. It's like they don't care. They just say it's a physical object because it can push you. Okay, they measured it. They showed that through an experiment that space and time, or time by itself, space by itself, pushed the gyroscopes aside, and change the axis of orientation there. Okay, so they did all this fancy stuff, and after all that's said and done, he still cannot tell you what space is or what time is. And in fact, here you have today's notions. Okay, see if I can find this here. These are confirmed by dictionaries and encyclopedias. This is what space and time are. So if you're taking notes, get a pencil and pen and write this down, because we're going to have it on the test on Friday. Here it is. Yeah, this is what space and time are. Outer space, or simply space, is the what? Expanse. Whatever expanse is the expanse beyond celestial bodies and their atmosphere. So what we have is an expanse, whatever that an expanse is. Outer space is not completely empty, okay? We don't care if it's empty or not. What is it? But they're saying, so they think it's a container, which is what Newton said originally. So they're treating it as a container. It's just a movable or a malleable container, right? Maybe like a balloon, I don't know, maybe. It is a near perfect vacuum, whatever that means, because what's a vacuum? Vacuum is made out of particles because vacuum is space. So I don't know what they're talking about. Unless they can draw this entity they call space, vacuum, nothingness, then we have no idea what they're talking about. Containing a low density of particles. Containing or made of? That's the question. I mean, is space a container, or is it made of particles, like this guy said originally? So they have all these contradictions. Space is a container, but it's a container of what? It's a container of atoms, etc., galaxies, whatever you got in there. But then space itself is made out of atoms, according to them. And so we have this circular argument. If it's made out of atoms, what's between, or about, not atoms, but particles, what's between the particles? Because when I have two particles, here I have two particles, right? Here, let's call these two particles. Well, hopefully there's space between them, because otherwise we wouldn't have discrete particles. There's got to be some medium that goes all around this ball for me to conceptualize this ball. And so if space is made out of particles, what's giving a background, what's giving what's contouring each one of these particles? So we still don't know what that stuff is that, gives shape to the space particles that come in from the void whenever the mathematician requires them. What is time? Well, let's find out. Time is the continued sequence of existence and events that occurs in an apparently irreversible succession from the past through the present and into the future. And the problem there is, if you look at the word past, present, and future, they're defined in terms of time. So we have a circular definition. Time is past, present, and future, and past, present, and future is time. Great, we've learned a lot. Defining time is in a manner applicable to all fields without circularity has consistently eluded the scholars. So that's a great way of ending your presentation. You start the presentation saying, we're going to prove to you and convince you that we know what we're talking about. And they end their presentation saying, oh, we're still researching. We have no idea what space or time are. But we know for a fact, through experiments, that the Earth drags time around itself, and so do you when you skate, turn around like a skater, twirl around, spin, you're dragging time around. Don't go into a carousel, a merry-go-round, because you're going to be dragging, time around yourself. And yeah, if you go to a carousel and spend some money there, you'll be spending a lot of time, believe me, you're dragging a lot of time around yourself. So that's the bottom line. They do these experiments and they come out with all these physical interpretations. When you point some of these things out to them, they end up saying, well, the fact is that all that's philosophy. We just do math. And then the question that you always should ask them is, why did you attempt to give a physical interpretation if it's not in your job description, if it's not in your line of work? Why did you give a physical interpretation? If you do equations and you call physics equations, no problem. But keep it within equation. Don't jump the fence into physics and say, I can tell you how the universe works, why it works the way it does. And you give they even illustrate it. And what they're illustrating is nonsense. They're illustrating what? That's what they're illustrating. How the Earth drags time around. That's what they illustrate. And so this is their conclusion. So you cannot say that these people have learned anything or know anything about time, that they can explain anything about how the universe works. And this is the bottom line, you know. So, all you can say is that they still know nothing.